So at this point, I'm assuming that unless you have been a serious hobbyist in electronics before joining the mechatronics course, you probably will not have access to an oscilloscope. So before I actually go and build this circuit on a physical breadboard and attach it to the function generator and the oscilloscope that I have for the video that's coming up, I wanted to give you an additional tool. Now, the simulation software at Tinkercad, it's fun, but it's not exactly designed for much more than fun. It's certainly not designed for research work, and while there are more powerful tools than this, one simulation software that I have found and I've started using myself is LTSpice. Now, if you do a simple web search for analog devices LTSpice, it'll bring you to this web page where you can download a completely free version of an open source SPICE simulation software, which is circuit simulation and analysis. The nice thing about this is that if you decide to use an Analog Devices IC in your design, their version of LTSpice actually comes with a very large library of the devices that you can purchase from Analog Devices. We're not going to be using any of those. We're just going to be using discrete components. I've already downloaded and installed this on my PC, so I'm not going to go through the steps. It's very straightforward. What I'm going to do is go through the quick step-by-step process of recreating our rectifier driven off of an AC supply and add on the low-pass filter with the components we just designed, and then take a few measurements. So once you've installed the software, open it up and go to File and create a new schematic. And I would recommend you immediately save it as whatever. Filtered rectifier. Using the software does take a little getting used to it. It has a slightly different user interface where instead of selecting the component that you want to do something to, you first tell it what you're going to do to the component that you're going to do it to, and then you select the component. So I'll walk you through this, and then you can kind of run on your own with any other experimentation that you want to do. As usual, it's a simulation, so you can't break it. Let's go through this step by step from beginning to end, and the beginning of this is our AC source. So in LTSpice, there are a number of components that you can just drag straight off of the top here. But for the power supply, we're going to have to go to Edit and pick up a component that we can then search for. We're searching for a voltage source. And the voltage source can be configured to be anything that you want. So once you've clicked it once, it does let you click multiple times to put multiple instances. If you accidentally do a second instance or a third instance of something that you intended to, again, like I said, it doesn't have you select the component that you want to do something to. You tell it what you're going to do and then select the component. So if we want to delete V2 and V3, we first press the delete key, which brings up the scissors, and then click on the components that we want to snip and snip away. So we have our voltage source, but we don't know what the voltage is. Let's right click on that. And if it was just going to be a voltage source, a DC, a stable, 5 volts, 12 volts, we could put it in here. We are creating an advanced source with a sine wave output, a 0 DC volt offset, an amplitude of 16 volts, and a frequency of 60 Hertz. although this is a simulation and therefore we could leave the load resistor, or sorry, the current limiting resistor out of the schematic, I'm going to go ahead and keep it in, just so that everything works the same from circuit to circuit, simulation to real life. So up here you can grab a resistor, and I'm sure you have the schematic somewhere in your notebooks, so you can very, very quickly replicate the schematic, and then we'll come back and assign values. So in the half-wave rectifier we had a current limiting resistor, and in the full-wave rectifier we had a current limiting resistor. In the half-wave rectifier we also had a load resistor, and I'll leave the load resistor for the full-wave rectifier until later. We need diodes. So in the half-wave rectifier we had one rectifier diode, and in the full-wave rectifier we had 4. One here, one there. These need to be rotated, so we can rotate those right now by going up to one of these. Rotate, rotate. And the second one is up there. D3 is a little off, so we're going to move it. In order to move it, we tell it we want to move something, and then we click on what we want to move, which I find a little clunky, but again, you'll get used to it. Pressing escape gets you out of the move, and then you can use the left click to pan to recenter, or you can use the scroll wheel to zoom in and out. Now let's add the load resistor. Load resistor. Rotate. And insert. Hit escape. And then in order to connect everything, you just grab the pencil. So we have the power supply going to the half-wave rectifier and the full-wave rectifier. We have the current limiting resistor going to the diode, and the diode going to the load resistor, and the load resistor going back to the power supply. And file, save. Now at this point we've replicated the original half-wave and full-wave rectifier minus the LEDs and without any output filtering. Let's assign a few values. So the resistor, for the load limiting resistor, we right click on the resistor and 330 ohms. Right click, 330 ohms. The load resistor is right click, 1000 ohms. Right click, 1000 ohms. In order to make a measurement, we need to know what the measurement is being referenced to. That is this symbol here, the ground symbol. So let's first look at our half-wave rectifier. So if I put the ground symbol there and I run a wire to it so that we can measure the voltage of the power supply and of the input to the rectifier and the output of the rectifier across the load resistor, we can now go up and simulate, run the simulation. And the simulation doesn't run continuously. It does all the math in the background and then presents you with the graph. So one of the things that you need to tell it is what the duration of the simulation should be. For a 60 cycle per second waveform, which has a cycle time of 16.7 milliseconds, if we want to see one full cycle, then we have to stop after, let's say, 20 milliseconds. I'm going to go ahead and do 100 milliseconds, so 0.1 second, to get multiple waveforms, multiple cycles on this waveform, on the output trace. Initially, you see absolutely nothing. But if you click on one of the wires, what will happen here is it will show you the voltage over time, in this case 100 milliseconds, of the point that you click relative to wherever the ground symbol is. So if we want to see the AC input, then it's relative to this point, and we want to know what the voltage is here, or really anywhere on that line. Anywhere you see that probe show up, you can click on it and read the voltage. And here we have our AC waveform with a peak voltage of 16 volts going to a negative peak voltage of minus 16 volts. And as expected, about here would be 16.7 milliseconds, which corresponds to one cycle. If we, with this trace, click another point on the schematic, we will see both of those points plotted at the same time. So we've already clicked on the AC voltage from the power supply. Now I'm going to click on the voltage after our current limiting resistor. And just like with the oscilloscope traces that you probably have already seen, on the half-wave rectifier, the voltage is different from the positive half cycle, where it is conducting through this 330 ohm resistor, versus the opposite half cycle, where it's not conducting. So on the positive cycle, there's a drop in the voltage. On the negative cycle, there's no drop in the voltage. And if we do a single click past the diode, then we'll get three traces. One trace being the full supply voltage, one trace being our second click of the input to our rectifier, and the third trace being this voltage across the load resistor. So now you can see that the negative half cycle has been clipped, and the positive half cycle is just a little bit under the input to the rectifier due to the voltage drop on the diode. If you want to clear this and only see one trace, you can do a second click on the same point. So now we're just looking at the output, or we are just looking at the input to the circuits as a whole. With the full wave rectifier, as you recall, we had to move the black clip on the oscilloscope probe off of the power supply and onto the resistor itself due to the diodes that are changing the characteristics of the reading at the output. But we're not going to do that just yet. So the input from the AC supply is of course the same for both rectifiers. And the input to the full wave rectifier is going to be from this point to the opposite point of the rectifier, which does include the diodes. So this doesn't necessarily need to move for this measurement. I can just click. At the input to the rectifier, because it's conducting on both half cycles, the 330 ohm resistor is reducing the voltage on both half cycles. So the green trace is the power supply, and the blue trace, which is now being reduced on both half cycles, is the input to our half-wave rectifier. In order to measure the output of our half-wave rectifier, though, we have to move our reference point. And press delete. And connect. And because I changed the circuit, the simulation needs to be recalculated again. So simulate, run, and click again. And now we see the output of the full wave rectifier, which includes both the positive and the negative half cycles, inverted to be both positive. In addition to measuring the voltage at various points, you can measure the current through various components. So if we were to measure the current through the current limiting resistor, you would see a positive cycle and a negative half cycle, and this little section in between the positive and negative half cycle where the voltage is less than the diode's turn-on voltage. And in the process, no current flows. As I mentioned earlier in one of my videos, the reason I chose the 1K resistor is because if I look at the current of the 1K resistor, then if the current is reading, let's say, 11.5 milliamps, then that corresponds to 11.5 milliamps times 1,000 ohms equals 11.5 volts. It just makes reading certain things much easier. So the half-wave rectifier is getting 11.5 volts across the load resistor, and if we zoom in on the peak here, then the full wave rectifier is just under the 11 milliamps that we originally calculated. Now, bear in mind that because voltage doesn't have a direction of flow, and if I, for example, click this point, it just simply shows me the voltage at that point. If I click this point, it just shows me the voltage at that point. But if I click a component, there is a current flowing through that component. And what determines the direction of this arrow, oddly enough, is not the direction of current flow. It is the direction that the part is placed on the schematic. So you'll notice that right now, if I was to click on the voltage across R4, it's going to show you a positive, because with respect to this point, it is positive. If I click on the component itself, you'll notice that the arrow is pointing to the left, which is toward the positive, which is wrong. It could be right in certain circumstances if we're talking about certain circuits that have currents flowing in the opposite direction of voltage periodically, but you haven't really gotten to that point yet, so we're not going to talk too much about it. The point is that right now, if I click this, it's going to show a positive voltage, but it's going to show a negative current. I can very easily just change that by going in and selecting that component, the resistor, and then rotating it. So now, when we do the simulation, if I click on this point, it'll give us a positive voltage, and if I click on this, then it will show us the current polarity relative to that direction. And ideally, with this being positive and this being less positive, then the current is flowing left to right, and when we click on that, we not only get a positive voltage, but a positive current. At the moment, you can't see the current because the scaling is exactly the same. When we were designing the circuit, I chose the 1000 ohm resistor because if you have 11 volts across a 1000 ohm resistor, then you get 11 milliamps through it. If you measure 11 milliamps, then you know that there's 11 volts across it. Or in the case of R2, our current limiting resistor, the current flowing through it is about 11 milliamps because, of course, it is essentially in series with the load resistor. But if you measure the voltage, it's not going to be 11 volts. It'll be 11 milliamps times 330 ohms. So you have to whip out your calculator and actually calculate those various values. With a 1000 ohm resistor, if you see 11 milliamps, it's 11 volts. So the next step is adding the filter. Since we are filtering the output of our rectifier, we do not want the load resistor to be directly connected to the rectifier. Press delete, snip, 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 snip. We need a resistor rotated, and I'm going to rotate this twice because I already know what's going to happen if I don't. The resistor choice was 330 ohms. Right click, grab a capacitor, and the capacitor was 0.0001, I believe. 100 microfarads. drawing a line, we're going from the input of the filter to the positive of our rectifier, the negative of our rectifier, is connected to the capacitor. The capacitor is connected to resistor. And then we have our 1K output. And that is connected exclusively across the capacitor. And reinserting our reference for measurement, it is going to be at the capacitor. So, if we now simulate this, and before we simulate, let's save this as, let's call it filtered rectifier 2. So now if we simulate this with the filter, we are going to see, relative to the negative part of the output of the rectifier, the positive now has quite an interesting change to it. At the beginning of the simulation, everything is at 0 volts. With the first half cycle, the capacitor partially charges. On the second half cycle, the capacitor charges a little more. On the third half cycle, fourth, etc., etc., etc. And eventually it stabilizes at some value. Let's make a little bit of a modification to the timing of this. So edit simulation command, and instead of stopping after 1/10 of a second, we will stop after 1/4 second. Simulate again. So it seems fairly stable after the first dozen cycles, dozen half cycles, which is half a dozen full cycles. And if we now add to the input to our filter the output of our filter, which is the voltage across the capacitor, you can see what happens. It starts at 0 volts. At each half cycle, the capacitor charges a little bit, until eventually it stabilizes at roundabout 5.9-ish volts with a low peak of 5.8 and a high peak of 5.98. So we have a peak-to-peak ripple of about 0.18 volts. And a DC value of about 5.92 volts. The ripple, by the way, is caused by the fact that the capacitor is being discharged continuously by our 1K load resistor. So if we also add in the current through the load resistor to this, we end up drawing approximately 6 milliamps through this 1K resistor I'm not going to show you what happens if you change or disconnect the load. I want you to play with this and find out for yourself and explain it to yourself. Because at some point you're probably going to have to explain it to the professor. Have fun. And one more thing. Once you've made a simulation like this, you can actually right-click on this screen and save it to a file. Export data as text. Choose what you want to export. Or more specifically, choose, well, it says right here, select waveforms to export. It'll come out as a text file with comma-separated values that you can then pull into Excel and plot and analyze on your own separately.